Hello to everybody, and welcome to this first installment of the tutorial of the Empirical Macro Toolbox. Let me share the screen here. Okay, so first of all, this is a joint product with Filippo Ferroni, which is the Chicago Fed. And in this first installment, I'll just give you a general overview of the structure of the toolbox and one particular set of commands that could be useful to decompose time series into trend and cycles or to date turning points. So let me move on. So what is this empirical macro toolbox? Well, it's essentially is a package which uses Matlab functions and routine to estimate a number of reduced form models and semi-structural models of the VAR type. And it can do this either with classical methods or Bayesian methods. And once estimation is performed, you can do forecast. As I already said, the toolbox also allows you to decompose observable time series into two latent components, which I'm going to call trend and cycle for simplicity. And it will also allow you to date turning points and to compute statistics of business cycle phases, such as amplitude and duration. Now, inference, you can do a lot of stuff with the toolbox. You can do inference on the parameter. You can do forecast, both point forecast and density forecast. You can study dynamic propagation of shocks. You can also do nowcast and mixed frequency estimation. And you can deal with large data set through system reductions and through large scale models. The codes, the source code with example are located at these two sites. The first site is a GitHub site and is continuously updated. The second one is my personal homepage, which I update once in a while. And there is a guide associated with the codes, which can be downloaded at the same sites. It's going to be called Hitchhiker Guide. So let me give you a general overview. What is in the package? So there's going to be estimation of VR, and an estimation of VR will be either classical or Bayesian. You can do a lot of stuff. You can do different identification procedure. You can compute the impulse responses, variance, and historical decompositions. You can do point and density forecast, as I already said. You can deal with missing data or mixed frequency of data. You can run VR with exogenous variable. You can even have panels of VR, and you can deal with time variant coefficient heteroscedastic models. There's going to be a part dealing with what they are called FAVAR, or principal component VARs, and these are going to be static versions of these models. There is a portion which deals with local projections, which is an alternative way, as we have seen, to produce a propagation mechanism. And there's going to be both classical and Bayesian estimation. You can do with these in this framework also density and point forecast, and it's going to be able to do structural kind of identification either via Cholesky or instrumental variable. And finally, there's going to be filtering methods, which, as I already mentioned, allow you to compute trend and cycles, dating business cycle, and computing turning points. So there's going to be about 14 different parts. I'm not going to go through the details. The important thing here is that for each part, there's going to be a bunch of examples in the source code that you can use both to practice and to see exactly how things are implemented. For today, I'm just going to talk about the first two, which is going to be dating turning point and computing cyclical statistics and trend and cycle decomposition. The next set of the next tutorial will deal with classical VAR, VRX, Bayesian VAR, and calculation of impulse responses. And the third tutorial will deal with large-scale VAR, FAVAR, panel VAR, and mixed frequency estimation. The last will deal with density forecast, point forecast and density forecast, and with local projections. So in case you're unfamiliar with Matlab, and I guess some of you may be, I'm going to start really from zero. So if you want to install the toolbox, you have to go to open your Matlab and then add the toolbox to the Matlab path. And you can do this in two ways. Either at the beginning of your program, use the add path command that you see in this line, and I'm assuming that you are storing the file you downloaded in this C user, and that the version that you're using is 4.2. Alternatively, if you don't want to do this, if you do this, you have to do it every time you run the program. If you don't want to do this, you can go through the Matlab home window and click on the set path icon, and there you can click on adding the folder with the subfolder for your exercises, and that if you save it, then it will stay there forever, and you don't have to do this all the time. There's also going to be a set of routines, optimization routines, which are written by Chris Sims, which have to be installed exactly in the same way. So either you add path to your script or your program every time, and the subfolder where the routine are is cmin tools, or you add it with the set icon path, set path icon. Once you have done this, the first thing you want to do, obviously, is loading some data. And here there is nothing new. There's a typical Matlab command. So if the data are already in Matlab format, you simply use the command load and with the data name. And that will be loaded into your workspace. And you can see exactly what is in this file that it's called data in the workspace window. If you don't have data in Matlab format, probably you will have it in Excel format or in any spreadsheet. And then you can use the standard Matlab command to read spreadsheet, which is Excel read. And you have to specify the file name and the sheet name in case you have more than one. If you have data which is stored in any other format and you don't know how to load the data, you can use in the Matlab window the help command with the command that you care about. So in this case, it's help load, and it will basically tell you what are the options which are available. So let me turn to the dating point exercise. So the dating point exercise is basically reproducing what's called the Brian-Boschen algorithm. And the implementation that the toolkit uses is the same as Pagan and Harding about 15 years ago. So if you want to do the turning point computation, you have to activate using this function, which is called date underline. And the date underline function takes as input there are 6 possible inputs, and there is an output which is called dt, which is a field which contains a lot of stuff. So y is obviously the data, time is the time span, assumed to be in years, Frequency is the frequency of the data, and it should be either M for monthly, Q for quarterly, or A for annual. And then T start and T end are obviously the beginning and the end of the sample, and they have to be reported in parentheses. So if you want to say the sample starts in 1970 quarter 3 and ends in 2020 quarter 1, then the command is in this format. So you have the year, space, and the month, or the year, space, and the quarter. And the final option, which is the final input, which is these options, is not necessary, but allows you to customize the dating function in a number of ways. So in the options, there are different sub-options. There is a phase options, there is a cycle option, there is a threshold option, there is a complete option, and a NREP options. So phase sets the minimum duration of the phase. So if you have quarterly data, then the minimum duration is 2 quarters. If you have monthly data, it's 6 quarters. Cycle sets the minimum length of the estimated cycle, which is either 5 quarters or 15 months. Threshold is a threshold which tells you to bypass the restriction 1 and 2 on the phase and the cycle, as long as the difference between the peak and the trough are large enough. So the default here is set to 10.4. The option complete simply considers only complete cycles beginning and eliminates incomplete cycle at the beginning or the end of the sample. And NREP is used in the case you are simulating data from a model, in which case you have multiple data sets. And the exercise that you are going to run is going to be not only on one particular data set, but on repetition of the same data set. Obviously, the default of this is 1, as the default of option complete is equal to 1. So the output of the function is dt is a field that contains a number of subfields or objects, which are the output. So it will have the subfield called st, which contains the phases. So sub st equal to 1 contains the expansion, st equal to 0 contains the contraction. Trinary is a trinary array which contains the states, which means the peak, the trough, or none of the two. Dura contains the average duration of contraction and expansion. Ampl contains the average amplitude. Cumulative contains the average cumulative change in contraction and expansion. And next contains the excess, which is basically the triangular area between the peak and the trough. The next three subfield simply compute the coefficient of variation across contraction and expansion for each of the statistics that we have mentioned. One thing that is missing from this list is the concordance of turning points, and this is not automatically computed. There will be an example in the tutorial which shows you how to do it. And the function date works on a single series. So if you have more than one, you have to loop the function inside a for loop. Let me turn. So this is basically everything that you need to do to date turning points. Instead, if you want to do trend and cycle decomposition, you have many options available. Some of these options are univariate, some of them instead are multivariate. Most of the options should be familiar to you. The first are really simple. The first one is using polynomial trends, and the decomposition is activated using the function polydet, which take as input y. Ord is simply the order of the polynomial, and the upper limit is 4, and gg is an indicator function that tells you if you want to plot the trend and cycle that you are obtain or not. And the output of the function are obviously the cycle, which is called dc, and the trend, which is called dt. The second one allows you to have a break in the polynomial. So the inputs of these functions are exactly the same, except there is a new one, which is called TT. TT is simply the date in which the break obtains. So the break, as I say here, must be selected in advance. There is no option at this point to do this recursively and estimate the break date. So you need to know exactly when you want to break in there, and the output are exactly the same as before. The third approach is differencing. There is no specific command for this, but it's visually easy to do in Matlab, so you will see it in an example. The fourth approach is what is now called the Hamilton local projection approach, and is activated using this function which is called Ham filter. Ham filter takes as input the data y. H is the horizon over which the projection is computed. Lags is the number of lags that you're going to use in the projection equation. FF is an indicator to tell you the function if a constant is included or not. And GG is the same as before, is an indicator for plotting. The output again is DC is the cycle and DT is the trend. Ham filter allows Y to be a matrix rather than a vector, so you can have n components in series. And at this point, the only thing which are allowed in the Ham filter function are lags of the dependent variable. So you cannot use other variables as a conditioning variables. The next one in the list is the standard Hodrick and Prescott filter. It takes as input the data and the lambda parameter, which is the smoothing parameter. It computes the trend. So the cycle is simply equal to y minus the trend. The typical value for quarterly data for lambda is 1600, and the corresponding values for annual data and quarterly and monthly data are 6.25 and 129,000. Now, as we'll see, one of the problematic things about the Hodrick and Prescott filter is that it's two-sided, which means it cannot be used in real time. So for real-time decomposition, you may want to use what is called a one-sided Hodrick and Prescott filter, which is activated with this function, one-sided HP serial. It takes as input again the data and the lambda parameter. You have the possibility of discarding some initial value. So there is a disk here, which is discarding the observation. Typically, as I say, discard is equal to 0. And the output is exactly the same. It includes the trend and the cycle. Now, the main difference between these two commands, as I said, is that the HP filter uses past, current, and future values of y to construct the trend. The one-sided uses only past and current value to produce the trend. The next two are bandpass filters, and there are two different implementations. First, the bandpass filter, truncated bandpass filter of Baxter and King, which is activated with the command BK filter. Y is the data. BP1 is the lower limit of the band, of frequency band, and BP2 is the upper limit of frequency band. So if you have quarterly data, you typically choose BP1 is equal to 8, which is 2 years, and BP2 equal to 32, which is 8 years. The BK filter generates the cycle. So if you want the trend, you have to subtract the estimated cycle from the trend. The Christian and Fitzgerald implementation is called with the CF filter. It has more inputs than the BK filter, so it still has the data and the upper and lower limit of the band, but it has 3 more inputs, which are CF1, CF2, and CF3, which basically set up a few options. So CF1 tell the filter whether the time series that you are considering is different stationary or trans stationary. So if CF is equal to 0, you have no unit root. CF2 is an indicator for a drift. So if you have CF2 equal to 0, there is no drift. And CF3 is basically chooses the format of the filter where you have 5 options available. Okay. If you don't specify CF1, CF2, and CF3, they are set to this value as a default. As an alternative to the bandpass filter, one can use also a wavelet filter, which is basically as a moving average filter, and is activated using the command wave filter. The inputs are the data, Y, and GG is a usual indicator function for plotting the data. Now there are two type of inputs, two type of outputs out of this function. There's going to be cycle and trends computed in two ways. One is using 8 to 32 quarters cycles, and that will be the case that you are summing up what is called D3 and D4, or 8 to 64 cycles, which you sum up D3, D4, and D5. And the trend that you are computing are correspondingly the difference between the actual time series and the cyclical component. For the Butterworth filter, there is no direct implementation in the toolkit simply because there are Matlab commands which allow you to do this. And if you want to see exactly what they are, just look at the manual. There are two unobservable component decomposition which are allowed in the toolkit. One is the standard one with the random walk trend and AR2 cycle, which is activated with the UC1 sub line here. And the inputs are the data and the options. The options are given here. So the implementation here is by Monte Carlo Markov chain. So it's going to do Bayesian estimation. So there are a few options which refer to the setting up of the Monte Carlo setup, which is NSIM and burn-in. There are a few options which describe the prior mean and the prior variance of the parameters, which are the last four. And then there's an intermediate option, which is called row yes, which if set equal to 1, allows for the trend and cycle to be correlated. If this option is not set, the default is 0. This decomposition may take some time because, as I said, is using Monte Carlo Markov chain method. The alternative decomposition allows the trend to have a local linear specification and the random walk, so it's more general, and it allows you to choose the specification of the cycle in terms of the AR parameter. So the composition is called with this UC2. The inputs are the data, the number of lags in the cycle, and the options, which are listed below. Estimation here is by classical maximum likelihood, and the parameters are listed in the order. First, the autoregressive parameter, then the standard deviation of the measurement error, if there is measurement error, and of the trend and of the cycle. The option, as I said here, are the initial set of parameter value, the initial set of variance value, the routine to be used for estimation, the upper and lower limits of the value of the optimization that you are willing to accept. And I'm sorry, I said the index in estimation tells you which parameter you want to estimate. And the max compute tells you essentially which maximization routine you're going to use. The last two decomposition instead are based on VERs, or one is univariate and two are multivariate. The univariate is the Beveridge-Nelson. It takes you activate it with BN univ. It takes as input the data, the number of lags, and then there's a bunch of indicator function here. They are the usual one. The most important is whether you're using a constant or not, ff equal to 0 or ff equal to 1, and if you're using the estimated mean or the long-run mean to calculate the decomposition. The bivariate or multivariate decomposition is that you are activated with this bn bq biv. Y could be a vector here, and lags is the number of lags. Rho yes is whether the two shocks are correlated or not, in which case the decomposition that is triggered is the one by cover 2006. And then you have a bunch of indicator function which basically determine this, whether the things, the data, which data are integrated and which one are not. So in terms of practice, there are two examples that you can take a look. They are in the tutorial, in the folder called Trend and Cycle Dating Tutorial. The first example dates turning points on a bunch of Euro and US area, Euro area and US variable, and aggregates the turning points using a simple counting measure. The second example instead is called example 1 cycles. Estimate the cyclical component of output and of a number of credit measures, and basically look at the relationship between output and credit over the business cycle. I think it's a good idea if you run the codes. There are a few little exercises in it. You can try them, and that will help you to acquaint yourself with the language of the toolbox and the Matlab syntax in case you don't know it. So this is the end of the first part. Hope you have found this presentation interesting, and you will play with the codes and with example. Happy trail.